Light makes photography. Embrace light, admire it, love it, but above all, know light. Know it for all you are worth, and you will know the key to photography. Not only photography, of course, but life itself. These words, spoken by none other than George Eastman, should be an inspiration to us all. But light, the essential element of life, is the most taken for granted. Air, of course, has the Clean Air Act enforced by the EPA, likewise water, but it seems no one ever thought to ensure that the quality of light should be guaranteed for present and future generations. It's time at long last to heed Eastman's admonition, know light. All of us, government, industry, consumers, all of us need to know and understand light, because the plethora of new artificial sources is producing nothing less than chromatic chaos. That the quality of light should be taken so for granted is due to the fact that for millennia there were relatively few sources of light, and what there was naturally produced. So there was essentially no choice for us humans to make. The nature and quality of light was a given. So what light was there? Well, for starters, daylight, which, while it may be provided with a myriad subtle hues, is essentially a constant or flat spectral power distribution. Firelight, candlelight, oil light, and so on, all, by the way, the visible heat of combustion, including, of course, that great hydrogen-burning fusion reactor in the sky, the sun. In the course of these remarks, I'm likely to express some frustration with officialdom regarding the subject of light, so let me temper my remarks by reminding us all how far we've come in just a few centuries. In ancient Greece, they actually thought that vision was caused by Aphrodite having lit a fire in our eyes that projected out and was reflected back from objects in front of us. Huygens totally wrong in terms of light, it was actually extremely prescient in that they anticipated radar. Later, Huygens, Young, and Newton clashed over their respective notions that light was a wave or a particle. And while they never reconciled, we were eventually forced to concede they were all right. As Einstein said, we have two contradictory pictures of reality. Separately, neither of them fully explains the phenomena of light, but together they do. In 1845, Michael Faraday had conceived the momentous theory that James Clerk Maxwell would codify 20 years later, that magnetic force and light were proved to have relation to each other. And so here it is, the electromagnetic spectrum, only a small portion of which is visible light. Within that spectrum, we can also describe the color characteristics of the light in what we call a spectral power distribution, the amount of energy at each wavelength. As we've described through most of our history, almost all of our light came from combustion, something burning. That common ground came in very handy for William Thomson, Lord Kelvin, when he determined he needed a way to be able to describe the different versions of light. He found that if you heat a piece of iron sufficiently, it will first turn dull red, and then, as the heat rises, will become progressively lighter and bluer in hue, so that the color could be described by the temperature of the iron or black body. There's a salient point to mention about this constant power distribution of light. Any way you look at it, it was here way before we were. So not only our eyes, but every creature before us that had eyes, going back some 600 million years, evolved their entire visual system from eye to brain around a constant illuminant, mainly the sun. And I hope to demonstrate how extremely important this is. In a word, color. We humans are immensely sensitive to color. A subtle change in the hue of a fellow human's skin alerts us to their state of health, in this case, jaundice. Likewise, we use color to assess the quality of food we eat. It's said that the Romans were the first to recognize that people eat with their eyes. And modern science has demonstrated that when a person sees food, neurons fire in the hypothalamus, beginning a chain reaction of hormonal release with the result that you become hungry. Unless, of course, what your eyes tell you about the food is that it's unfit to eat, which will bring about the opposite reaction, a feeling of revulsion. Quite subtle differences in the color of gemstones, like diamonds, can significantly alter their value. An army of color scientists employed throughout industry attest to the market value of skillfully applied color technology. Your car interior has parts made from different materials such as plastic and fabrics and produced in factories far and wide, but must represent an appearance of uniform color and do so both at night in artificial light and during the day in daylight. My particular interest in light and color, and the reason I'm here talking to you today, is art, especially, of course, cinema, the movies, but any visual or graphic art, even fine art. Here's just one small example of the significance of light in art. These are, of course, Monet's studies of haystacks. He takes one perhaps common and prosaic item, the haystack, and with it he conjures a host of perspectives and perceptions and moods. There are some 25 paintings in the series. I once had the distinct and rare pleasure of seeing many of them in the flesh at the Musée d'Orsay in Paris, where they'd been gathered together. The reproductions we're looking at here hardly begin to display the nuance and subtlety and vividness of the originals. But even so, the range and scope is readily apparent. But what are they saying to us? Well, they speak to us of the very essence of art. Art is revelatory. We're propelled into this world, and in our intense need to comprehend it, our place in it, and our experience of it, we reveal in myriad ways what insights we have to one another. We inform ourselves and share with each other that insight. When objective, prosaic discourse like philosophy is inadequate to that task, we resort to more subjective, figurative, and evocative means of communication, such as religion, and ultimately and arguably the most effective, art. The essence of art is choice, selection, perspective, a point of view. And of course, as Monet demonstrates, there's an infinity of subtlety available to the artist. The art of cinema involves myriad choices, and beyond the obvious story, character, etc., many involve the images the audience will see. Here are images from Stanley Kubrick's 1975 Warner Brothers film, Barry Lyndon. If nothing else, Kubrick is the master of zeitgeist, his films conjuring their time in history like few others. He's also a fanatic about it. With Barry Lyndon, he demanded that many scenes be shot with only the light that would have been available in the period, which, being the 18th century, dictated candles. No camera at the time was able to accomplish such a feat, so Kubrick enlisted Ed DiGiulio of Cinema Products. Here he is in a Warner short, Stanley Kubrick, A Life in Pictures.
It originally was a lens manufactured, designed, developed, and manufactured by Zeiss for NASA. And of course, NASA was planned to use it in satellite photography. And for that reason, it's an extremely fast lens. It's an f/0.7, which is 2 stops faster than the fastest lenses that are available even today. Of course, Stanley's intention for these lenses was to shoot the famous candlelit scenes in Barry Lyndon. And that being the case, he shot with the lenses wide open, f/0.7. And as a consequence of that, he had practically no depth of field at all. And it was quite a chore to do it, but of course, the images were absolutely gorgeous.
With the introduction of panchromatic film in 1927 and the incandescent light, spectral power distribution in lights and spectral response in film stock assumed greater significance. Even though the film was black and white, the spectral reflectance of the whole color gamut was discernible, as shown in this illustration of color reproduction by the then new panchromatic film. These events occurred at the time of the birth of the Academy. This illustration was taken from an extensive study, the Incandescent Report, launched by early academicians in 1927. With the advent of color cinematography, the bar was raised from significant to critical, with even slight changes in spectral power distribution becoming evident. By the early 50s, incandescent light at 3200 K had been adopted as the de facto design illuminant for color film, unless the intended source was daylight. By the 70s, these had been codified by the ISO in a series of standards culminating in the current ISO 7589.6. With the advent of digital cinema cameras, the same design illuminants were maintained, and this has persisted to the present, though what has also persisted to the present is the desire of each camera designer to distinguish his camera from any other. As of the NAB 2016 convention, camera manufacturers still illuminate their demo sets with tungsten incandescent sources rather than the SSLs on abundant display by luminaire manufacturers in adjacent booths. The salient feature of the tungsten incandescent lamp at 3200 K that recommends it as the design illuminant is its smooth, continuous ascending curve, its spectral power distribution, or SPD. This smoothness is shared by the other design illuminant, daylight, which is distinguished by its higher temperature. And both of these sources, when they radiate on an object, permit that object to produce the full spectral reflectance or color they possess. This smooth SPD is also a very forgiving circumstance when integrated by the spectral power response curves typical of cinema senses, both film and digital. The amount of energy captured by the sensitivity curves will certainly differ from one maker to another, though the differences will be relatively subtle. By contrast, the discontinuous SPT of discharge sources can lead to quite radical changes in radiant energy on the subject, and thus the luminous energy recorded by the camera. So what happened to disturb the beautiful symmetry of our natural light sources and precipitate us into the chromatic chaos we're experiencing today? Efficiency happened. Energy efficiency. Just over 200 years ago, Sir William Herschel discovered that the sun radiated more than just light. I know. You just spend a few minutes in Death Valley and you'll make the same discovery. But before Herschel, people thought that heat was light itself. What Herschel discovered was that the sun radiated something invisible to our eye and hot. He actually made the discovery because he was studying the spectrum via a prism and trying to characterize the different colors by their temperature. Inadvertently, he set the thermometer outside the area lit by the prism in the relative dark next to the red portion of the prism's beam, and found its temperature rising where he would expect it to go down. He quickly realized he was seeing sunlight that was invisible but detectable by its heat alone. He called them calorific rays, what today we call infrared. Indeed, fully half the sun's energy that reaches us is in the form of heat. And so it is for most of our natural sources of light, firelight, candles, even our faithful tungsten light bulb. For much of human existence, that wasn't an issue. But then the 18th century ushered in its double whammy, the Enlightenment and the Industrial Revolution. We owe a great deal to both of these. Indeed, the United States owes its very existence to them, but they were and are a double-edged sword, for they precipitated us into a ferocious desire for more of the one thing that cannot be manufactured: time. Our intellectual and industrial appetites increasingly consumed first our days and then our nights. Artificial light, we discovered, could extend and expand our days to be more productive. The oil lamps like these had been with us for thousands of years. They burned a variety of oils, including whale oil. But commencing in the 17th century, we decimated the once gigantic whale population. We moved on swiftly to fossil-based fuels such as kerosene and gas, first coal gas and then natural gas. And then around 1890, we began to see artificial light in the form of the electric incandescent lamp. So far, everything had been producing more heat than light, and so we moved on to the gas discharge lights, starting with the mercury vapor light. The graphic we're looking at is from a tool that allows us to assess color rendering of different light sources, which we'll discuss in more detail in a little later. Here we're illustrating in the lower portion the SPD for tungsten. Above it, we can see a standard Macbeth color checker chart depicting the color rendering produced by tungsten light. Here's the same chart illuminated only by the mercury light. A characteristic of this light was its blue-green color. The tool allows us to split the Macbeth chart in half horizontally, enabling us to display the two color renderings resulting from comparing mercury and tungsten. And curiously, the mercury discharge was in a way the inverse of tungsten in that it mainly emitted a very short-wave UV around 250 nanometers. By 1940, we had a version of discharge light called fluorescent, in which the basic mercury vapor plasma, the short-wave UV at 250 nanometers, was used to excite phosphors coating the inside of the discharge tube. These phosphors provided light in additional bands, so the light began to emulate natural light. Somewhat. The efficacy and economy of artificial light was skyrocketing, as was its use. But as efficient as fluorescent light was, it was not a point source and didn't lend itself to directed, focusable fixtures. Moreover, it employed mercury, which was deemed hazardous. Way back in 1907, Henry Round, an engineer working for Marconi on vacuum tubes for amplifiers, observed a phenomena in the form of a faint light emitted from a carborundum crystal. In 1927, Russian scientist Oleg Losev determined that it was not a thermoelectric effect, in that the luminescence was cold. It produced light without heat. By 1962, James R. Beard and Nick Holonyak had each produced the red LED and predicted LEDs would replace the light bulb. But we had to wait for Suji Nakamura's creation of the blue LED in 1993 for the white LED to become possible, and a huge technological revolution was underway. And it needed to be. Here's a look at the proliferation of light at night over a period of 18 years. The International Energy Agency has estimated that 20% of global energy is devoted to lighting the planet, and the cost is over $230 billion. Governments around the world have reacted with alarm to the prospect that at this rate we will light our way into oblivion. Thermoelectric sources like incandescent are being legislated out of existence. Early on, the compact fluorescent lamp, the CFL, invented by Ed Hammer in 1976, seemed the logical choice, but these also entailed the toxicity of mercury. Thus, the arrival of Nakamura's blue LED seemed like the holy grail. The US Department of Energy pumped at least $75 million into research into LEDs with the aim of providing a massive increase in the lumens per buck, and the industry responded. In 2014, Isamu Akasaki, Hiroshi Amano, and Shuji Nakamura received the Nobel Prize in Physics for the invention of the efficient blue-emitting diodes, which has enabled light and energy-saving white light sources. The late Dr. Roland Haits provided us with Haits' law, which posits exponential increases in efficiency for LED lighting, with corresponding decreases in cost per lumen. In their zeal to adopt the cool, efficient light of the LED, they overlooked some important facts: the relative complexity of the power supply and the discontinuity of the spectra. They also overlooked the possibility that we actually hadn't exhausted tungsten technology. As MIT recently pointed out, a tungsten filament surrounded by a photonic crystal will recycle the excess heat and convert it into light, thus reducing both the heat and the energy per lumen to a point competitive with fluorescent and LED, and restoring both a ludicrously simple power supply and the smooth, continuous SPD of tungsten. And they evidently didn't consider plasma, whose roots went back even further than the LED, all the way back to Nikola Tesla in 1894. So while it is possible to build an LED light that can describe a continuous spectra, such as the spectrally tunable room Philips produced for the NIST lab, the cost ran to $12 million. To achieve the lumens per buck the DOE as well as governments around the world were demanding resulted in a discontinuous quasi-white light. A practical demonstration of discontinuity in the movies is a shirt that turns from blue to maroon when the actor moves from a fluorescent light deficient in deep red to a tungsten light rich in deep red. Here's a more subtle illustration from the experiment produced by the SciTech Council. The dress combined both blue and teal colors in the fabric. Lit by the continuous illumination of incandescent on the left, the subtle interplay of the blue and teal was evident. However, illuminated by an LED, the dress appeared plain blue. While the urns do not have quite the same distinction as the dress, nonetheless, there's a discernible difference between them. The LED was using a blue exciter LED to excite phosphors to produce an apparent white light. But the spectral trace of the lamp revealed a dip, or lack of energy, in the cyan region adjacent to the blue spike. The history of the motion picture industry is littered with the laments about the lack of understanding of such issues as continuous and discontinuous light, of spectral power and color rendering, as well as the need for more adequate descriptors and indices than CCT and CRI with which to describe the quality of light, especially the color rendering properties of light. In their 1948 SMPE paper, Spectral Characteristics of Light Sources, Norman Macbeth and Dorothy Nickerson said, quote, "While illuminants are often referred to in terms of the color temperature, it is their spectral characteristics that produce a specified result," close quote. Well, here is what Crandell et al. Had to say in their 1949 SMPE paper on the issue of discontinuity. Quote, "We are interested in a continuous spectrum which will not show any unpleasant surprises with colors having narrow absorption or reflection bands," close quote. For all their concern about discontinuity in their day, they had no idea how daunting it would be to characterize the chaotic LEDs. However, the French CST, the Superior Technical Commission for Image and Sound, defiantly undaunted, recently released an impressive study of some 28 lights. A wealth of data is provided, a spectral power trace, and several indices. The BBC issued this statement with their 2014 low energy guide. Quote, "Although the correlated color temperature can be similar to that of a tungsten source or match the daylight color temperature, the spectral composition also has an effect on colors. If a light source lacks a particular wavelength in its composition, that color could not be rendered," close quote. After years of ignoring a substantial body of professional expertise in this area, a couple of years ago, the Department of Energy did finally acknowledge much of what we said in a report entitled Solid-State Lighting, Early Lessons Learned on the Way to Market. Quote, "Existing metrics pose a challenge for LEDs which can have different SPDs compared with conventional light sources and can be either near or far or away from the black body locus. Additional metrics are needed that characterize all light sources and simplify complex information. The lighting community should establish meaningful criteria that can balance color quality with energy efficiency goals," close quote. We welcome their somewhat belated comprehension of the issues and are delighted to respond to their admonition to address them once again. But before I do, I need to point out that in the DOE discussion of indices in their early lessons paper, they omit mentioning their own index, the CQS, or Color Quality Scale. This scale favors the higher color saturation inherent in many LED lights, as if to say, it's not a bug, it's a feature. After all, don't we all want to live in a Technicolor world full of bright, saturated colors? It's possible they omitted the CQS because they were about to release yet another effort, the IES TM30, which promises a much more comprehensive capability. However, TM30, as with most such indices, relies upon a standard observer in the form of a human, which is a problem for us folk in the cinema world, as I shall explain momentarily. However, at this point, I don't want to be too hard on an agency that is vital to this country, yet may be slated for extinction. DOE sponsors more research in the physical sciences than any other US federal agency. The Academy SSL project proposed a new index, the Spectral Similarity Index, or SSI. Since conventional indices break down with discontinuous sources, we chose to create a power index pegged to the SPD of tungsten at 3200K. The other compelling reason is that color rendering indices like the CRI are based on the human eye as the standard observer, whereas in cinema we have cameras as the observer, and none of them are standard. They're all different. Cameras assume a design illuminant 3200K tungsten. If that illuminant deviates, then so will the color rendering. So if you can characterize any deviation of the spectral power distribution, you can likewise characterize a color rendition deviation. No matter how good an index may be, it's only able to provide a guide to the suitability of a given light. For more precise analysis, additional tools are needed. And so the SSL Committee of the Academy began to develop a computer modeling program to analyze the implications of discontinuity in motion picture lighting. Eventually, we hope that it will be possible to make it generally available as an open source multi-platform tool. It will be useful not only for cinematographers, but for lighting folk generally, including the engineering and manufacturing community of the lighting field. Let's take a look at a brief overview in which Joe DeGennaro explains how it works.
It was immediately determined that this new tool, which we're calling the Academy Color Predictor, would be of great value to anyone who works with modern lighting devices. A spectral power distribution measurement is recorded and uploaded into the program. This data can be immediately compared to the spectral power distribution of any other light source recorded in the program library, and their compatibility can be evaluated in correspondence with the spectral sensitivity data of whichever film stock or digital camera is selected. The comparison is easy to visualize because instead of mathematical formulae, we see color-accurate images showing the true look that would result from combining these light sources on set. Aside from the standard Macbeth chart, there are a number of other virtual test targets to choose among. For those who rely upon them, there is also an immediate listing of 3 different test metrics, CCT, CRI, and CQS, for whichever light source is chosen. There are added features that allow testing of things like the white balance, camera filtration, lighting filtration, and in addition, one can view some very sophisticated mathematical graphs in a 3-dimensional environment to help visualize the direction of color shifts that occur between the light sources being tested. This trilinear plotting feature is especially valuable for predicting whether post-production color correction can be relied upon for adjusting differences in color rendering between 2 test sources. In some cases, when the shifts are parallel, color correction will succeed admirably. However, when there's divergence in the direction of these shifts, color correction in a DI suite would be a costly and ineffective solution. One final feature will be an obvious benefit to those who design and build solid-state lighting units and their components. It enables one to create a virtual lighting unit, selecting any number in combination of emitters with an infinite capability of spectral power distribution, aiding in the potential to invent new lighting technologies with more accurate color rendering ability.
We said at the beginning that these issues affected not only photography, of course, but life itself. As kids, many of us played with flashlights like this. What's apparent here is that various types of radiation can travel right through us. X-rays are an example. I think most of us are aware that we synthesize vitamin D in our skin via exposure to sunlight, or the UVB component of sunlight. Photosynthesis, of course, one way or the other, provides most of the food we eat. About a dozen years ago, NASA began to publish their work with phototherapy, or red light therapy, for wound healing. Around the same time, we learned that for decades we'd been exposing infants in hospital nurseries to inappropriate light. Infant retinas are especially vulnerable to the 436 mercury line found in fluorescent lights. Obviously, not all radiation is beneficial to us. Shortwave ultraviolet can damage our eyes, our skin, interact adversely with some medications, and even alter our DNA. Mercifully, we're protected from most of this by our atmosphere. A few months ago, the American Medical Association issued a report on the now massive use of LEDs for street lighting. Quote, "The new AMA guidance encourages proper attention to minimize detrimental health and environmental effects," close quote. Here's a satellite view of the city of Milan, where the city center is noticeably illuminated with daylight-balanced LEDs versus the yellower light of the suburbs. Most life forms on this planet have some form of circadian clock. Well, your body also uses light as part of that process, and it expects to find essentially bluish light during the day, becoming yellower toward the end of the day. We evolved into the creatures we are today, bathed in electromagnetic radiation, and are biologically utterly dependent on it for our very existence. We were designed for the spectrum of electromagnetic radiation that permeated our world since long before we inhabited it. It would seem abundantly foolish and more than a little irresponsible, now that we have a handle on the physics and photobiology of light, to be reckless with how we provide it. From our discussion today, and by the way, we'll post this discussion on the PICFAIR website where we'll welcome your participation, I don't think we're faced with onerous technological hurdles so much as a failure to comprehend. All it takes is to care sufficiently for the subject, and as George Eastman said, we must strive to know light.